Okay, so we left off last time. We had just essentially given some foundation for thinking about probability. And when we're generally talking about probability, we're going to reference back to this idea of the cardinality of S over the cardinality of A over the cardinality of S, where A is some subset of S, right? S is the sample space or the containing set of A. And we can think about this as the probability of A. One of the things that, one of the places where we put a little bit of foundation, and I want to expand on this a little bit, is this idea of drawing with replacement. And this was, we counted in cats, dogs, and ferrets, for instance. I think goldfish was one of those as well. So if we're thinking about drawing an item with replacement, we can think about, well, we have item A, B, and C. And if we're going to draw two of these items, two of these elements with replacement, we can make an exhaustive list of these, right? Where CC, CB, CA, right? And then we've got BC, BB, BA. Then we've got AC, AB, and AA. And we can see that, this is indeed exhaustive, and we can think about this as a counting system. This would be what we might refer to as a base 3 counting system. Base 3 in more cases is going to look like this. It's going to look like 0, 1, 2 if we want to make this numeric. And, maybe if we're talking about two places of base 2, I'll start with this as our lowest character, 0, 1, 0, 2, and then we've got 1, 0, 1, 1, 1, 2, and we've got 2, 0, 2, 1, 2, 2. Keep in mind, this is not really different from base 10. If we're talking about base 10, we've got 0, 1, all the way up through 9. And we can say 0, 0, 0, 1, right? And all the way down to 0, 8, 0, 9. And then we roll over that 0 to 1, right? And we get 1, 0. Don't know why that keeps happening. Then we get 1, 0, 1, 1, 1, 2, all the way down to 1, 9, and then we roll over to 2, 0, and so on. So this harkens to this idea of drawing with replacement, which is sort of our fundamental idea of counting. We're going to expand on counting and think of counting as another angle, as the paired, as the complementary approach to our set formulations, right? And we're going to think about three things here. We're going to think about factorial, permutations, and combinations. So let's start off with factorial. I think factorial is, it's this common operation, mathematical operation that we know we can perform, right? We know how to do this. But I'm going to make kind of a case for why factorial exists here. If we think about 5 factorial, or let's think 5 factorial. So this is simply 5 times 4 times 3 times 2 times 1. And, we can figure that out. That's 120. And notice there's a way, there's a different way we can think about this than just this is a mathematical operation, right? There's something a little bit more about this. This is the number of ways. This is the number of ways to arrange 5 unique items. And it may not be obvious, it's going to take a long time for us to arrange 5 items. I have to write out 120 things to really be able to do that. But we can make a case for this, for factorial, from basic counting, okay? So let's think about this in terms of, let's think about this in terms of base 4, right? So 0, 1, 2, 3. How many different ways can we arrange this? Well, we can approach understanding that by first counting, okay? So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 1, 0. Actually, let's only do three places of this. 0, 1, 1, 0, 1, 2, 0, 1, 3, and then we can go 0, 2, 0, 0, 2, 1, 0, 2, 2, 0, 2, 3, and 0, 3. You know what I'm going to do? I'm going to just do 2 places because otherwise we're going to be here all day. So we can go 3, 0, 3, 1, 3, 2, and 3, 3. So if we're thinking about this, well, if we're just trying to arrange these 4 items into any 2 arrangements, right? We select 2 of these, then we're going to get rid of anything that has duplicates in it. And we can then see how many arrangements of 4 of these items into 2 boxes, right? Notice this is without replacement. And so, thinking about this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 ways we can arrange 2 of these. Arrange 4 of these into 2, into selections of 2, right? So when we're really thinking about this, there's kind of an emergent algorithm that we're going to start seeing. Let's do, instead of a base 4, let's do a base 3, and let's put this into the form of a story. There's a nice slide for this as well. So let's think about an urn, right? We're always talking about bowls and urns and bags, and there are 3 numbered balls, right? So there's ball 1, ball 2, and ball 3. And we're wondering how many different ways can we, or what are all the different ways that we can pull balls out of this urn, okay? So we can either select the first ball, or we can, on the first draw, so first draw, or we can select the second ball, or, ball number 3. And then we're going to draw again. So we have the second draw. So from the second draw, we've got 2 possibilities. We're either going to select 2 or 3 if we've already selected 1. We're going to select 1 or 3 if we've already selected 2. And we're going to select 1 or 2 if we've already selected 3. And then from here, well, we can see that there's only one thing left on the third draw. So we can just fill this in pretty easily. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. And we can see here that there's 1, 2, 3, 4, 5, 6, right? And 6 is indeed 3 factorial in that it is just 3 times 2 times 1. So this is going to hold for however many numbered balls are in this urn, or however many different items that we're trying to arrange. This can get a little more complex than that, but I just want to show that a starting point can be from simple counting, right? So let's do this. 1, 1, 1, 1, 1, 2, 1, 1, 3. And this is exhaustive and a little bit exhausting, but we can do this. So 1, 2, 1, 1, 2, 2, 1, 2, 3. And then once we get to there, we're looking at 1, 3, 1, 1, 3, 2, 1, 3, 3. And then we start with the 2s, right? So we have 2, 1, 1, 2, 1, 2, 2, 1, 3, 2, 2, 1, 2, 2, 2, 2, 2, 3, 2, 3, 1, right? And 2, 3, 2, 2, 3, 3, and then this should be the last of these. So 3, 1, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 2, 2, 3, 2, 3, 3, 3, 1, 3, 3, 2, 3, 3, 3. And we can, from this point, after our basic counting, we can then reduce the space by eliminating anything where there's duplicates. So there's duplicate 1s. Eliminate any place where there's duplicate 1s. And there, and there. And duplicate 2s. So there's that. Here's duplicate 1s, 1, 3, 2, 1, 3, 3. There's duplicate 3s. 2, 1, 2, that has duplicate 2s. 2, 1, 3. 2, 2, 1, 2, 2, 2, 2, 2, 3. 2, 3, 1, 2, 3, 2, 2, 3, 3, 3 is duplicated. 3, 1, 2, 3, 1, 3 has duplicates. 3, 2, 2, 3, 2, 3 has duplicates. And there's all those. So the thing about this, doing this by hand, is I'm probably going to make a mistake in here. I probably crossed something out that I shouldn't have. Let's find out. Oh, no, I got them all. And so here is another way, right? Here's an algorithm where we can see the emergence of 3 factorial, right? There's 3 factorial results when we look at this. So we can start with our raw counting, and then we can reduce the space. And this may be something we would consider a brute force algorithm, right? It's fairly computationally expensive depending on what we're trying to do, but it does seed the idea and give kind of a foundation for how we're going to think about factorial. The first thing that I'm going to have you code is the factorial function. This is one of those functions that we expect you to be able to kind of, wing offhand before very long. If we're like, hey, code the factorial function, that is sort of like a rudimentary accumulator pattern. And yeah, don't worry if you can't get it within 3 minutes. That's fine. We're going to write factorial a few more times, at least 3 more times in breakouts. So I'm just going to put 3 minutes on the timer and go ahead and code factorial. All right, I'm going to start coding this. I noticed a lot of people got a factorial function in that time, which is great. So I'll say def factorial, and we're going to take the factorial of, I'll just do n here. Maybe I'll make this a little bit bigger. And I'm going to start off with a product that I'm going to collect into, or I'm going to multiply by, a range of numbers. And because I'm multiplying, I have to start at product gets 1. So I'm going to say for num in range, and we can go ahead and start at 2, even though I could start at 1. I'm going to start at 2, and I'm going to go to n plus 1 to be inclusive of n. And I can just say prod times gets the number, and we can return the product. So let's check the factorial of 5 just to make sure this is working. And let's also check the factorial of 0. So, just a quick statement here. Think about this idea. 0 factorial. How many ways can you arrange 0 items? Well, there's only one way to arrange 0 items, right? So that's a way if you have a hard time remembering that 0 factorial is 1, just remember that. There's only one way to arrange 0 items. Okay, let's see if this works in the way that we expect it to. And let's see, am I in the right place? Yeah. Okay. And we get 120 for factorial of 5, and we get 1 for 0. Now what happens if we say factorial of -10? So that shouldn't be defined, but notice our function is returning 1. I could proof this in some way. I could say, if n is less than 1, throw some kind of error. But I'm not going to worry about that. We're not going to be generating any cases where that's going to be a problem. Okay. So I've got here. Let me paste that into the Slack for anybody who didn't get to a solution. And now we're going to apply this idea in another breakout. All right, so there are 10 people standing in line for beignets at the world-famous Café du Monde in New Orleans. How many different ways could the 10 people be arranged in the queue? We're assuming that these are all individuals with... Given that the line was formed organically, what is the probability that they are standing in the queue in alphabetical order? And we're assuming everyone has a different last name, and we're arranging by last name in alphabetical order. So I'm going to put 3 minutes on a timer, and do your best to answer this question. Okay, so let's think about how to answer this. The first thing to notice here is that we have 10 people. And if we're thinking about the exhaustive way to arrange 10 people, that's as easy as factorial of 10. The next part of this may not be immediately obvious. What is the probability that they're standing in the queue in alphabetical order? Well, the different arrangements, how many different arrangements are there? Well, there's, we could say the magnitude of S is going to be factorial of 10. How many different arrangements are there where they're in alphabetical order? Well, there's only one, right? So the magnitude of A, as we'll refer to it here, is just 1. And we can see that the probability here is just the magnitude of A over the magnitude of S. And we can print that and see what that is. So how many different ways to arrange 10 people? That looks like 3.628 million. And the probability that they'll be arranged in alphabetical order is really tiny, right? Like this is a very small number. And I think in light of the number of different arrangements, we can see why that would be a small number, right? There's only one way out of 3.6288 million, right, that we can arrange them in alphabetical order. Okay, so we're probably going to continue to come back to this magnitude of S, magnitude of A idea. We're going to think about it that way, but we're going to approach this with counting. Why is the magnitude of A 1? Sure, yeah. So if we're thinking about this, in terms of arrangements, and let's say we have Andrew, Billy, Catherine, Dorothy, Eli, Frank, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, IJ. And let's just imagine I said names for all of these. There's only one way, right? There's only one way to arrange that many, or arrange those people in alphabetical order, and it's like this: A, B, C, D, E, F, G, H, I, J, right? And since there's only one way, then that's our subset. This is the only item in our subset, this arrangement. And so in that case, A, the magnitude of A, the cardinality of A is going to be just 1. And, with that, the cardinality of S is going to be the, exhaustive number of arrangements. And that's going to be 10 factorial. That's why that ends up being such a tiny number. Okay. So factorial leads us into another idea. Okay. There's a factorial is sort of the special case for what we call permutations. Okay. So if we have 3 items, A, B, and C, well, let's call it top, yo-yo, and how about pog? If we are trying to arrange these, what are all the different ways we can arrange these? Well, that would be we take these 3 items and we can permute them into 1 arrangement, 2 arrangements, or 3 arrangements. And 3 permute 3 is simply 3 factorial, okay? We select the top and then either the yo-yo or the pog, or we select the yo-yo and then either the top or the pog, right? And we can see that that's 3 factorial. But consider that we can permute 2 of these items, right? 3 permute 2 is going to be, it's not going to be 3 factorial. It's going to look something like this. So we've got the possibility of choosing either the top or the yo-yo or the pog, and then the top, after the top we can either choose the yo-yo or the pog. After the yo-yo we can either choose the top or the pog. After the pog we can either choose the top or the yo-yo, right? And we can see that we've got, ty, tp, yt, yp, pt, and py. That's 1, 2, 3, 4, 5, 6. Well, how do we sort of close this up mathematically? This is kind of the thing that leads us to understanding this idea of we've got this many items, like 3 items, and we're permuting 2 of them. Well, we're reducing the space from 3 permute 3, right? And if we're reducing that space, we can actually do this fairly systematically. And maybe one way to see this is through the idea of 3 permute. Let's look at this through 3 permute 1. How about that? And if we're thinking about 3 permute 1, then we can pretty easily see how this is going to go. It's going to be, either the top, the yo-yo, or the pog. Why is that? Why would that be the case? Now, we could even take this a step further into 3 permute. Oh, it's a different pen. We could say 3 permute 0. 3 permute 0 is, how many ways are there to arrange, 0 items? Well, there's only one way. And so if we step back from this, how many ways can we say 3 permute 1? Well, we can think about this 3 factorial first, and we can reduce that space. We can say that this is actually going to be 3 minus, let's say in the case of 3 permute 1, this is going to be 3 minus 1 factorial. And if we start breaking this out, we can see that we are indeed reducing the space pretty effectively. And what that looks like is 3 times 2 times 1 over, 3 minus 2, well, that's 2 factorial, 2 times 1, right? And we can eliminate these, and we're left with 3. So this is fairly systematic. It's kind of really nice, actually. We can generalize this formula and see that n, which is the number of items, let's say, permute k, where k is the number of items that we are selecting, is just going to be n factorial over n minus k factorial. We can just think about this bottom part as reducing the space, right? So there's this many arrangements, but then we are reducing by this many arrangements. So let me check Slack. Okay, yeah. Okay. So we've got this permutations formula, and I'll just go ahead and put this up here. N factorial over n minus k factorial. Something that we say here is that order matters. And maybe that seems obvious at this point. Well, the way that we've arranged people in this line, Andrew, Betty, Kat, however we've arranged them matters, because that's the order that they're in line. That's actually that's the crux of our issue, is how do we arrange this group of people. And so we can say, the order here matters. Notice that when we do this, we've got, let's say we have 10 people. Well, how many different ways, or how many different possible types of permutations can we have? Well, we can have 10 permute 10, 10 permute 9, 10 permute 8, 10 permute 1, all the way down to 0. And what we're doing as we do this, 10 permute 10 is going to be a larger value than 10 permute 9, and we can pretty clearly see that. Okay, so we can discover permutations in the same way that we discovered factorial. And I'm going to kind of outline a simple enough algorithm for the discovery of permutations. I already kind of did with this reductive approach, right? But let's think about the first step, where we count in the base n system, right? So the way that we talked about that was 0, 0, 0, 0, 0, 1, 0, 0, 2, if we're talking about 3 items, and then 0, 1, 0, 0, 1, 2, 0, 1, 3, and so on. And we make this exhaustive idea, right? This exhaustive count where we might be considering with replacement, right? We draw a value and we put it back, and then we potentially draw it again. Now, the next part of this is we can reduce numbers, right? What I'm calling numbers here, by removing duplicates. And, that's like in the case where we had 0, 0, 1, let's say. Well, this wouldn't be valid, right? Because we've got 0 in there twice. And so if we're drawing without replacement, then we can't draw 0 twice. So this wouldn't be valid. However, 0, 1, 2 would be valid, or 0, 2, 1, or 2, 1, 0, or 1, 2, 0. Those would all be valid. And, from that point, we can discover the number of permutations by simply, take k, what I'm going to call digits here, though that's not quite the right word. Take k digits from the right. So if we're talking, this three values in this case, right, where we have 0, 1, 2, and 2, 1, 0, and 0, 2, 1. If we're talking 3 permute 2 in this case, where we've got 3 items and we just want 2 of them, well, all we really want from this is these 2 rightmost items. So this would be 3 of the permutations of 3 permute 2, 1, 2, 1, 0, and 2, 1. That's not all of them, right? But that's 3 of them. So this general algorithm, again, this is a brute force approach. And what we have up here is a mathematical approach, right? We've got this permutations, n permute k is just n factorial over n minus k factorial. So really quick, I'm going to have you code the permutations function. And then we're going to kind of, we're going to jump down a few rabbit holes through this lecture. and we're going to go down one of them in just a moment. But first I'm going to have you code the permutations function for n permute k. So let's put 3 minutes on the timer. Actually, let's do 3, right? Remember, this is going to be dependent, obviously, on your factorial function, right? We've got n factorial over n minus k factorial. So you're going to call back to that function. So go ahead and code that out. Okay, so I'm going to code this out really quick. Put this down here for the moment, and there we go. All right, so if I'm thinking about this, I think we're calling this just permutations, right? N permute k. This is simply, we can return the factorial of n divided by the factorial of n minus k. So that should work, and why don't we test this with, let's print the permutations of 10 permute 10, which is going to be, should just be 10 factorial, and let's print the permutations. The other one we looked at was 3 permute 2, I believe. Okay, so we can see here, this is that 3.62 million, and we can see here that this that 3 permute 2 is 6. So I think it's safe to assume that this is working. Notice I'm getting float values out of this, and this is counting. So I'm likely just going to wrap this in an integer call, right? Because it doesn't make sense for that really to be a float. It should be a an integer. So this is one form that this function can take. I want to show you a slightly more optimal form, and this is going to be a theme of this lecture. We can take this form and we can improve upon it a little bit. And this is going to look like a little more code, but it's going to be able to handle larger permutations, and we can kind of check this if we want to. So this is going to look quite a bit like the factorial function. I'm going to create this accumulator for the count of permutations. And I'm going to say for I in range, and I'm going to go from n down to n minus k. And I'm going to travel by -1. So I'm going to start, let's say if we're doing 10, I'm going to start I at 10 and then go 9, 8, 7. If we're doing 10 permute 6, then we're only going to go down to n minus k, which is going to be 4, right? And we're going to bound at that. And that's going to be less calls to this kind of factorial operation. We're not actually using the factorial function. We're including some reduced number of operations here. So we can do, let's return perm, and I'll just call these again to make sure that that's still working. Now, why would this matter? Why would this make any difference? Well, what happens when let me demonstrate part of why this could matter at some point. Let's do 50, let's do 500. Why not? Let's see if that actually... So notice all these zeros right here. This is a huge number, by the way. Notice this is some massive number that we're able to see here. But at some point, we get all these zeros at the end. We are going to get less zeros using this more optimal form of permutations. What these zeros represent is the inability to store an actual value. We've just made this number so huge that we're throwing away the end. And maybe I can demonstrate this difference really quick. Well, we can't even do 500, permute 500, using our factorial function because integer division result is too large for a float. So there's that. So we can't even handle 500 permute 500. We can't even start to handle it computationally with our prior function, but we can handle it with this. And there's some utility in thinking about why this might work a little bit better, and I can demonstrate this pretty easily here. So let's say we're dealing with, and I'll do my best to answer that question that's in the Slack regarding how would I explain 10 permute 10, for example. Let's think of this as in terms of 10 people, right? So we've got some 10 people, like again Andrew, Beth, Kathy, etc. And we've got 10 of those people. So let's say n is 10. And let's say that there's only 4 of them. Let's say only 4 of them are going to be able to get served at this bagnette stand in New Orleans. So it does still matter which 4 of them, right, and what order they're in. So what order they're in matters. Who's going to get served first, who's going to get served last. So we could say that we have a k of 4. Now, if we plug this in to our function, our permutations function up here, we can see why there's some utility in rewriting the algorithm in this descent sort of way. This is going to be 10 factorial over 10 minus 4 factorial. Well, let's break this out. Well, first, this is 6, right? 10 minus 4 is 6. So this is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is going to be over 6 times 5 times 4 times 3 times 2 times 1. We can start crossing these out. Well, why would we bother, right? Why would we bother doing this multiplication operation and making this huge number that we then divide into this other even huger number on top when we can just eliminate anything here that can just be canceled out? And we see that this operation is actually much simpler, 10 times 9 times 8 times 7. So that's what is reflected in this other way of writing this algorithm. And then what we get out of that is a count of how many different ways, right, that 4 of those 10 people can stand in line at this sandwich stand. Okay. So, I'm going to skip this next breakout and let's take that general kind of algorithm for permutations, the one that I did by hand where we, count in the base n system and then we reduce the space by removing outcomes where there's duplicate items. And I have a kind of a coding prompt here. So we have 5 pets and 5 beds. What are all the ways that you can arrange those 5 pets in 5 beds? So let's make some pets here, and I'm going to explicitly call this base 5, and let's have I don't know, salamander and fish. It's like a fish bed, and I'm taking way too long to do this. Okay, dog and a bird. How about that? Oh, let me answer that question. Yes, I will paste in the permutations function. So I'll put in both of these. All right, so we're going to think about the different ways of, what are the actual different arrangements? Not necessarily how many arrangements, but what are those arrangements? And to do that, I'm going to take this reductive approach. So I'm going to say animals counting and make that an empty list in which I'm going to collect all the different ways if we were to count these animals with replacement. So for animal 1 in base 5, and then I'm just going to do this 2, 3, 4, 5 times. And then I can say animals counting dot append, and I'm going to append this list that has animal 1, animal 2, animal 3, animal 4, and animal 5. And I do have to change those names. So 5, 4, 3, 2, and 1. And now we can look at this. So for each animal number in animals counting, we can print the animal number. And we can take a look at this. And we can see, looking at this, we're counting from, there's a lot of these, right? Anybody want to throw out a guess as to how many these are? Oh, there we go. So we start at salamander, 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 and then we go up a number, salamander, 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 fish, and we count all the way to bird, 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 bird. So that may seem like a strange number system, but it's what we've got, and we can work with this. And yeah, the number of these that exist is as stated in the Slack, it's a base 5 system. We've got 5 places of it, so there's 5 to the 5 different numbers here. And if we want to verify that, we can say, let's print 5 to the 5th power, and let's print the length of animals counting. And we should be able to verify that. 3,125. All right. So from here, the next step is to reduce the space, to take out values where there's duplicates. And we can do that. We can just traverse animals counting and pull out the strict permutations, right? The permutations, we don't have repeats in permutations. So let's do animal perms, and we'll say for each animal number in animals counting, let's assume at first that the animal is a permutation and we'll reject it if otherwise. Okay, we'll switch this flag to a false if it's not. So for each animal in animal number, if that animal number has a count of that animal greater than 1, right? If there is a duplicate, then we can go ahead and set permutations to false, and we can break. And if permutations is false, well, it doesn't matter, right? We're going to, look at the next animal number. We know that that's not a permutation. However, if it is a permutation, then we can say animal perms dot append. We can append that animal number. One nice thing about this approach is that we get to see the pattern, an emergent pattern of swaps. And what I mean by swaps is since we don't have duplicates, two animals will be swapped with each other. And we can even start analyzing that. We can write an algorithm based on that. And if you think about it this way, if we are swapping, we don't have to do this initial count, this initial exhaustive count where we start at salamander, 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 salamander. Shoot. There's so many syllables. I don't even know if I said that, 4 or 5 or 6 times, right? And, we don't actually have to do that. We can find a better algorithm. And I'm going to show you a better algorithm for doing this. So first, though, I just want to see the idea of such an algorithm by looking at the different animal numbers themselves. So let's print this animal number, and we should see how many permutations there actually are. So I'm going to just scroll up to the top of this and grab a chunk of these. And let's kind of just take a peek at how these do actually swap. So hopefully I can write on this. So bird, notice bird is moving here and dog is moving here. And then in this next one, bird moves back and dog moves all the way over here and cat moves here. So it's hard to see an emergent pattern, right, at this point, but there is a pattern here. And we're not going to implement this pattern necessarily, but I just want to show you that because of the way that we've counted through these, there is a pattern. And we can systematize that pattern and use a swap operation to make an algorithm that will perform much, much more efficiently on this problem than the algorithm that we just wrote. So, we could continue down this thought, right? Bird moves here, dog moves over here, cat moves here, and everything else so far has been consistent. And, bird stays in its place, and then dog and cat swap. And now, fish enters the ring, and things start changing. And again, you could systematize this. There's a better algorithm than that, and I think I'll code through that after we take a quick break. So let's take in just a moment. We'll take a break. I'll look at questions. There's a question. Does anybody understand unexpected EOF while parsing? EOF here just means end of file. So you might be missing a closed parenthesis somewhere. that's often why we get an EOF. If you paste in your snippet, I can try to diagnose what's going on there. Okay, I'm going to set this timer for 6 minutes. I'll see y'all back here at that point, and then I'm going to code through a better permutations algorithm for getting the permutations out of a set of values. Okay, so I'm going to implement heaps algorithm for permutations. And when I was referring before to this idea of swapping, well, here we've got 4 items, right? A, B, C, and D. And we can see some kind of systematic swapping pattern. Now, this isn't the same swapping pattern that we were seeing with seeing through the reductive approach. This is a different swapping pattern, and I think it's slightly more efficient on in its implementation in code, and that's part of why we would do that. So we've got here we're swapping A and B, and then we're swapping B with C, right? And we can see some kind of systematic approach. Now, we're not going to necessarily talk about the the computational, the time complexity of this algorithm or anything like that, but it's pretty safe to say that through a swapping approach, we're going to have a more efficient algorithm. And I also want to say that you will not need to code anything at this level of complexity, but I want to show it to you because this is part of where you're headed in data science, in programming in general, right? This is going to be the kind of thing you get handed an algorithm. You get the handed well, here's the algorithm for a random forest, and you kind of have to come up with some data, and then you have to implement a random forest from scratch, using NumPy arrays and the way you think about the problem. And to give you a sense of this, let's look at from that article. There's an algorithm that they provide, and it's rather large. I'm trying to fit it all in one screen. You know what? Yeah, I think I can do that. Here, let's try this. So this is what I'm going to call a non-recursive algorithm. And all I mean by that, we're not going to cover recursion, but recursion is when a function calls itself and it kind of builds a stack of operations that it then unwinds to deliver a result. And it turns out that this problem it actually lends itself really well to recursion, but we're going to take a non-recursive approach. And the reason for taking the non-recursive approach really for us is in order to better understand what the algorithm is doing. I think recursion is hard to grasp upon first look, even though you end up with a lot less code. So let's talk about what this is going to do. We're going to pass in n and an array, just an array, which is a list in Python. A list is a type of array. So we're going to pass in a list, and we are going to store the progression of items in something we're calling, well, really it's kind of a stack. Well, we're calling it a stack state here, but we're going to have numerical encodings for the positional values of the items in the list that we pass in. And here we're going to continually perform swaps and until we are exhaustive with one layer of the swap operations. And down here we actually we end up resetting stack states, or kind of this storage array. So I'm going to do my best to talk this while I code it, but I also don't want to put a lot of time into it. This is more to give you a sense of an idea, give you an idea of the kind of baptism by fire that happens in the DSI, where you're thrown an algorithm and you're like, I have no idea how this works. And then you figure out how it works and you write code and you make that happen. And that becomes your daily paradigm, for a good chunk of time, right? You're going to end up coding a neural net from scratch, a convolutional neural net from scratch. You're going to be coding a lot of different algorithms from scratch. So I want to give you a sense of what that might be like. Let me look at this. Oh, okay, cool. It's just checking Slack really quick. All right, so one of the things that we're going to use here is a simple swap algorithm. And there is a, well, arguably, I think there's a better way to write this, but I'm going to write it in a longhand in order for it to be understandable. So we're going to swap two indices in a list. So we're going to pass in a list, and we're going to pass in an index and another index, right? So I think that's pretty straightforward. And I'm going to make a copy of the list. This is going to add a little overhead to this algorithm. If we were implementing this in a language like C or some lower level language, we'd probably modify it in place, but we're not going to worry about that. So I'm going to store one of the items in this list. I'm going to store index 2 into a temp variable. And this is a very classic comp sci algorithm thing to do. You're like, oh, well, we're swapping something. Let me take that and put it in a temp variable. There's a more compact way to write this in Python, but I'm just going to leave it in this longhand. And then I can go ahead and directly swap in for index 2 the item that's in index 1, right? Because I've set aside the item that was in list sub index 2 into this temp variable. And then after that, well, this is easy at this point. Notice that the value that's in index 1 is now in both index 2 and index 1. But I want to take that index 2 value and put it into index 1. So I can just put temp in like that. And then we can return this list. So let's just try this really quick. Let's print the swap of, let's do A, B, and C. And let's swap 0 with 1 and see if that works. Oh, not timer. So now we get BAC, right? So that's a pretty direct, we understand that is working. All right, so now let's get into the algorithm itself. And I'm going to title this heaps non-recursive. Again, there is a recursive algorithm. Feel free to read through the article. I think there's a lot in there that can be really fun. Also, we're not going to make anything this hard on the technical interview. So, if you're working toward the technical interview, I would maybe hold off on digging deeper into this. So again, I'm going to avoid modifying the parameter, and I'm just going to make a copy of the list, and I'll do it like that. And now I'm going to hold the stack state, which is just for every item, there's going to be, we're going to store where it's been. And this may be, I don't know if you've seen this syntax, but I am going to, for every item that's in the list, like the length of the list, I'm going to make an entry in C. And that's where we're going to kind of store what's happening. And now I'm going to collect the permutations into something called perms. And I'm even going to snag that first permutation, which will be the first thing that we see. Okay. Now, why am I putting K in there? Well, K is we're going to take the front part of each of these permutations that we generate. So if we've got 10 items and our K is 10, we'll just get all of them, right? If we've got 10 items, if we have an N of 10 and we have a K of 6, well, let's just get those first 6 entries in the list. So I'm just populating this initially with our first item. So we're going to have this thing. This is our. This is a little bit of jargon. This is our stack pointer. So this is what we are working with, what item we're working with at any time. And I'm going to say while I is less than the length of the number of items in our list, we're going to do stuff. So for entry, for this initial entry of I in our stack state, we're just going to perform the operations that will satisfy heaps. And so the first thing is if I is even, then I am going to swap the 0th place with I. And then if it's odd, I'm going to make a different swap. I'm going to swap the value that's in C sub I with I. This is the heart of this algorithm. It's just a little logic game. And ultimately, like everything else from here is kind of gravy, you know. So let's look at this. If this value, if the permutation that we're considering here is not already in our permutations, then we can put it in there. So perms.append and list copy. Right, notice I've got up until k, you know, this is a consistent thing. So it might even occur to you that if we're trying to arrange 10 items into k spaces, this may not be the most efficient algorithm. It's going to be definitely efficient, more efficient than what we did, but we're doing extra work here, right? We are going to have redundant work. So it doesn't mean that this is the most efficient algorithm, but it is pretty efficient, and it is underlying a lot of things. I think it's actually used in iter tools in the Python library. So I'd have to double check that. You know what? Don't hold me to that. So let's say at this point we can increment a counter, the counter C, for that position I. And we can then reset I. So I gets 0, and then if we didn't satisfy this condition, if C sub I was not less than I, if it was equal to or greater than, then we reset the state of I to 0. So let's do that. Reset state of count state at I. All right, C sub I gets 0, and I gets incremented by 1, and then that should actually be our permutations. So why don't we snag this animals, this base 5 of animals, and see if this works. So we'll pass in base 5, and we'll get all arrangements of that. So I'll just call that arrangements, or about 5 permute 5, and I'll say for each 5 in 5p5, let's print that. Hopefully this works, and it looks like it did. So that's nice. Notice, remember when we were seeing that initial A swap with B? Salamander and fish are swapping, and then salamander stays where it is, and fish and cat swap. right? And this is systematized, and it's actually easier to understand, to write this one out or to map this one out in terms of how these are being traversed than it was when we did the reductive counting approach. But notice to the far right here, we've got certain emergent patterns, right? We've got, bird stays consistent, then fish stays consistent, then cat stays, and dog stays, and salamander stays. That's not accidental. It's actually pretty cool, right? So we could check this for, take this same idea, and let's do, we'll change 5s to 3s. Actually, let's do this. For 3, and let's see if this works. Ooh, that may not have worked. Interesting. Let me just see. I may have an error. Oh, yeah, I definitely do have an error in my code here. Let's copy up to K. You know what? I'll have to troubleshoot that afterward. Well, either way, we're able to get a very quick permutation of 5 across 5, which is not everything that permutations should do, but it is a lot of it. So, okay. So let me just reiterate, you don't need to know how to do that right now. And it's awesome if you want to dig into it and figure this out. Oh, 5p5 should be changed to 5p3. That's what was wrong. Okay, let's see if that, you know what? Let's just back up, and thank you so much for noticing that. Now, let's watch this hopefully not fail. Oh, hey, it's always, whenever you live code something and it actually works, it's a cause for celebration. But yeah, we can see that this is working as expected, which is pretty cool. All right. Thanks. Okay, so now we talked permutations. We can take permutations a step further in terms of reducing the space. And that leaves us with combinations. Now, in combinations, well, let's think about this approach. If we're reducing the permutation space, let's say we've got 0, 1, 2, right? And we can say 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 2, 0, 2, 1, 0, 2, 2, and so on. Okay. If it doesn't matter what order these items exist in, then we can reduce the space, right? If we think of 0, 1, 2 and 0, 2, 1 as being the same thing, right? We have 0, 1, 2 and 0, 2, 1. Well, that's the same thing. Then we don't care about the order anymore. Now, it's interesting here because if we're talking about the combinations, of 3, where we're choosing 3 of those items, well, kind of turns out that this is going to be 1, okay? There's only one way to choose, 3 items when you only have 3 items. Now, that kind of means that we're not really going to do 3 choose 3. We're going to do something like 3 choose 2. And that means that we would eliminate this left side, right? And we can start thinking about, well, what are the different ways that this can appear? Well, 0, 0 is not valid, right? We can't have duplicates. 1, 1 is not valid. 2, 2 is not valid. And so we've got 0, 1, we've got 0, 2, we've got 1, 2. And I believe that's it, right? Am I misthinking anything here? Oh, we have 0, 2 as well. Nope, I already put that. Okay. 0, 1, 0, 2, and 1, 2. Yeah. So we have reduced the space further, right? If we think of 0, 2 and 2, 0 as being the same thing, right? We've selected the same two objects, then we want to reduce our space further. And, you know, let's take permutations, right? When we were talking n permute k, this looks like n factorial over n minus k factorial. If we want to make this into n choose k, we're going to just reduce this down a little bit further. We're going to reduce it by k factorial. And if you think about it, that kind of makes sense, right? If we're looking at all the ways that duplicates can, arrangements with duplicate values can exist, it turns out that is k factorial. We can divide that out from this n factorial. So that's our combinations formula, n choose k. And let's think about this in terms of the type of problem you might be solving. Let's say you have, I don't know, 10 toys in a bag. And they're all unique, right? They're all different. And you're going to have kids at a party pull out 3 toys from the bag. How many 3-toy combinations are there? You can see it doesn't matter here what order they pull them out, right? If it's, you know, I don't know, hacky sack, doll, fire truck or something, that's the same thing as fire truck, doll, hacky sack. It's not actually different. That kid is still ending up with the same 3 toys. A classic way to think about this is in terms of cards in, you know, a hand in poker or a hand in a card game. In general, if you've got a 5-card hand in poker, well, it doesn't matter the arrangement you have those cards in your hand at all. It doesn't matter. It's really up to you how you want to put them in your hand. And we can ask this kind of question, well, how many different 5-card hands are there in a game of poker? You know, that would be a combinations problem. And so with that in mind, I'm going to have you code the combinations function, right? And again, you could take that prior code from permutations and that more optimal code, and you can adapt it just slightly for combinations, or you can, you know, implement it directly as it is here. And I'm going to give you 3 minutes to do that. And I'm also going to paste in that heaps algorithm code right before I start the timer. Again, this is just for you to play around with and figure out the algorithm if it interests you. And yes, order matters in permutations. Think about permutations as arrangements that you can take a certain number of items from. And combinations is like a selection, right? Where it doesn't matter, right? You go and you buy groceries. It doesn't matter the order in which you buy groceries. It's some combination of groceries at the end of the day, or ingredients for a meal that you're preparing. You need those ingredients. It doesn't matter what order you put those ingredients. Well, it does when you're cooking, but the way you represent those ingredients in terms of making some food doesn't matter. Okay, so I'm going to set 3 minutes, and I'll paste in that code. All right, so let's go ahead and code this. So let's call this combinations. And we're just going to do n choose k. And that's how we usually say this, n big C k, n choose k. We're choosing any items in any order. And we can return the factorial of n divided by the factorial of n minus k multiplied by the factorial of k. And again, I'm going to wrap that in an int call. If we want a slightly more optimal version of this, that's going to look like, very similar to what we saw before with the more optimal permutations function. So this is going to be, I'm just going to collect with perm and say for I in range, and we'll go n down to n minus k in a reverse, and we're going to update, we're going to multiply the permutations by I. And then instead of just returning the permutation, this time we're going to return the permutation divided by the factorial of k. So notice that we still have this float limitation that we could run into potentially when we do this. So just keep that in mind. Yeah, and there's actually a more optimal way to write this, but I'm not going to explore that here. It's a little convoluted, and it's only marginally optimal. So if we think combinations, what was the prompt? 10 toys in a bag. How many 3-toy combinations are there? Well, let's find out. So combinations of 10, choose 3, and let's print that. 120. So that may, I think sometimes these kinds of counts are not exactly intuitive, Now, what does it look like when we increase this to 4 toys? Oops. 210. And what happens when we increase it to 5? I think this is the kind of thing that might be fairly interesting. So let's say for k in range, and let's start at 1 and go up to 10. We'll include 10. And let's see how this changes. I think this is often a really helpful thing to do, to look at how things grow. Oh, wait a minute. What am I doing there? K in range 1 to 10 plus 1. 10 choose 1. Yep. Oh, that totally makes sense. Yeah. And I think this gives you a sense of kind of a distribution in and of itself, right? And we can start thinking of building these spaces, right? Because maybe we're going to select 2 toys, maybe 4 toys, 6 toys, and maybe we're trying to maximize the number of different arrangements of these or combinations of these. Yeah, it's normal distribution-ish. Yeah, totally. And that may be a little bit surprising. And it might not be. And we're going to relate combinations to binomial very soon. Not in this lecture, but in one of our upcoming lectures. Okay, so let's, in the same way that we built that permutations intuition, let's build kind of a similar intuition around combinations. And with this, we're going to build, we're gonna start counting, right, in that same way that we did before, in a base system, in a base n system. And then we're going to create a list of the permutations, and then we can reduce out the permutations that contain the same elements. And the way that we can do that is we can sort them, right, and then remove duplicates. And that's something that will be fairly easy. We can see how to do that. So let's have a prompt here. This is what I'm going to call an expensive counting approach. And the prompt here is going to be, I have it here, let me just paste this in. Out of a set of 11 basketball players, only 5 can be on the court at a time. What are all the combinations possible for that basketball team? So, like I said, this is an expensive counting approach. And then we're going to look at a slightly less expensive sampling approach. And that might there might be some things about that that are a little bit surprising when we look at it. All right, so the number of combinations here, well, we can check that. We can say that's 11, choose 5, right? So let's set that aside and make sure that the function I'm about to write is working correctly. So I'm going to call this basketball combinations, and we're going to build all of the we're going to build the set of potential numbers for 11 numbers. And let's say we're just going to be, we're going to have players 1 through 11. And we'll keep it simple like that. So first we're going to get every arrangement of 5. And I'm just going to do that with a simple collector. And we can do a nested loops here in order to count. So I'll say for I in 11 nums, j, k, l, m, and possible 5 dot append I, j, k, l, m. And at that point, we could take a look at these, right? For each 5 in the possible 5, we can look at that. That's just our permutations. Okay, so, oh, I'm sorry. That's not our permutations. That's our counts. That's our draws with replacement. So now we can build our permutations. And for every 5 in possible 5, we're going to get rid of anything that has duplicate players in it. So I'm going to do this slightly differently. Remember the list set trick? I'm going to say if the length of the list of the set of 5. So the set of 5, if I do that, I'm going to remove duplicate elements. And then I cast it back to a list. I don't actually have to do that, but just to be clear on it. And then I look at the length of that. And if the length of that is 5, well, then that's a valid permutation. And I can say perms.append 5. So this is different from the way I did it before, but I just want to give you 2 examples of how you might do this. And I'm going to say for each 5 in our permutations, and I'm not going to run this. We're going to assume that this is valid permutations. I'm just going to leave it in there. And when you run it, you can uncomment those to take a look. So now we can build out our combinations. And this is the new thing that we're doing. This is the new part of our brute force algorithm. So the sorted 5 is going to get the sorted of 5, actually. This is all happening in a for loop, my bad. So for each 5 in perms, the sorted 5 gets the sorted version of 5. And then if the sorted 5 is not already in the combinations, then we can say the combinations, let's append to that the sorted 5. And again, because we're taking this very brute force approach, we're actually able to see an emergent pattern. And I think that's kind of a cool thing about taking a brute force approach. It's very systematized, and we can break it down. We can actually discern other algorithms from it. So I'm going to say for 5 in basketball combinations, let's print every 5. So this should be all of our combinations of 5. If I was actually printing it. What am I doing? Let's make sure something is happening in this function. Okay, there's definitely something. See if I can troubleshoot this really quick. Okay. All right, so our permutations, perms.append 5, the list set of 5 for each 5 and possible 5. If you see an error in here, definitely let me know what that is. I'm missing the range function. Oh my gosh. Well, that would do it. Let's see if that worked. Okay, cool. And did you see that there was like a little bit of a delay there, right? It was like, thinking about it, and then it gave us a result. And kind of a cool thing here is that we have this is systematic, and we can see that, okay, well, that first value is going to stay 1 for a really long time, and then it's going to change, and 2 it's going to stay 2 for much less time, right? We've already used a bunch of instances where with 2, and so we're going to have 2 not be the first item in this list for very long, and then 3 for even less time than 4, 5, 6. And 7, notice 7 only appears as the first item in the list 1 time. And that's, it doesn't matter what order these are in, but that we're seeing them in this kind of order is indicative of the underlying process in the algorithm. And I think if you were to pick this apart, you could write an algorithm that would have swaps in it and drawing from the pool of items. So that's what I consider to be an expensive counting approach. Let's look at really quick if we have time. I think we have time for this. Let's look at a somewhat expensive sampling approach. And in the same way, we're going to build 5-player samples from 11 players. And let's see how this looks. So I'm going to say from random import choice. Normally this goes at the top of the file. I'm just going to put it here so that it's in context. And let's call this basketball combinations sampling. And this is going to be interesting because we can actually change the size of the team with sampling, and we can change the number of players easily with sampling. It's not that we couldn't do this with a counting approach, it's just we would likely need to use recursive algorithms if we used a counting approach. So, or we would probably want to. So we're going to make a collector for the combinations, and I'm going to say our player range is going to be, of course, the range from 1 to team size plus 1. Okay, so while the length of this combinations, okay, is less than, and I'm going to utilize the combinations function from earlier, while this is less than the team size, the combinations of the team size choose number of players, right? Like 11 choose 5. We're going to do some stuff. So the first thing I'm going to do is build a player combination. And to do that, well, that's we're going to use sampling for that, right? So here's a nested while loop. It's sort of, a small coding atrocity. You know, you don't really want to do this, but I think it's appropriate here. We could do for loops with arbitrarily large values, 100,000 calls or something like that, and use a break statement. That would be completely legitimate as well. But either way, it's a nested loop, and you want to try to avoid those. We could find a different way to do this, but I think this is pretty straightforward. So while the length of the player combination is less than the number of players, we can grab a player number, right, randomly. And this is just going to be a choice from the player range, right? If we have 11 players, this is going to be between 1 and 11 that we draw. Now, if the player number is not already in that player combination, right, we don't want duplicates, then we can append it to the player combination. So player combination dot append player num, and this is us building an instance of a team. Okay. So from there, we can, I'm just going to overwrite this because that's fine for what we're doing. We don't need this in the order that it was in. So I'm going to get the sorted version of itself and replace it. And at this point, I could have just called this team. Maybe that would have been, maybe that would be easier to recognize, but I'm going to call it player combination. So if this team, this player combination, is not already in the combinations, then let's watch this as it's happening. So I'm going to print this as it's being populated. We can say combinations.append that player combination. And this is going to be surprisingly faster than you might expect, given that we are randomly pulling stuff, and we're gonna make a bunch of random draws that don't work, right? It's gonna be like, oh no, that player's already in there. Oh no, that team combination is already in there, right? And those are sort of wasted cycles. But I just want to make a case. Well, I'm going to continually make a case for sampling as a way to approach solving problems, especially problems that are computationally not very feasible with the machine you're on. Okay, so let's say we have a team size of 11, and the number of players is on a team is 5. Then I'm not going to. We're going to see output as this runs, so I'm not going to traverse the list that gets returned. Instead, I'm going to print the length of the, what is that function called? Basketball combination sampling, and we'll pass in the team size and the number of players. And we can also print, what that should be, which is just, we'll call the combinations function and pass in team size and number of players there as well. Okay, so let's see how this does. Combination is not defined. That's up here. Yes. Combinations. Let's try that again. Team size is not defined because I called it teams size somewhere. Right there. Okay. Okay, so that was really fast. Notice that these are in no particular order, right? We're not getting the emergent the emergent pattern. We're not going to be able to discern an algorithm from this necessarily by looking at it, because sampling kind of obfuscates what an algorithm might be. Like, we're just randomly pulling things in. So let's do let's do 21 choose 5 and see how that does, just to get a better sense of what might be happening here. So notice this is running, and make this a little bit bigger. And at some point, this is going to start slowing down because it's going to make a draw, that is it's going to continually, it's going to be much more likely as time goes on that it's going to make a draw that's already in those combinations. And we could even go so far as to do some kind of analysis on that, right? As we, like here, we can see it slowing down. There's a lot of loops happening in the meantime, and while it's slowing down, we could analyze the probability at various points in this process of drawing a new or novel team combination, right? And this is probably going to take, well, I honestly don't know how long this is going to take. I don't think it really takes as long. I think it probably doesn't take more than a couple minutes. But I just wanted to show, oh, wow, that was it. So we were able to solve, get this, we were able to solve this problem fairly quickly. I think I was talking maybe a minute and some change, a minute and a half at the most. And that's 20,349 combinations that we were able to produce through a sampling process. If we were to do this with that nested list counting process, it would be significantly longer than this. And that might be surprising to you. But that has a lot to do with the reductive approach being much more, having a higher time complexity than the cycles that we're throwing away through a sampling approach. And that just sort of verifies what I was positing earlier, is that sometimes intractable problems can be approached through this kind of sampling approach as opposed to using a kind of closed form counting approach. But if you have mathematical formulas, that's, going to get you there way faster every time. Okay. So what I think I'm going to do, there's a slide that I kind of want to go through, but maybe I'll save that for our next class and do it at the beginning of the class, because I think it's fun. Or I might just record a quick video of it and append it to just a quick 5-minute video. Hey, let's code a better combinations algorithm. So if you were to look at Python's itertools, and I'm just pulling up the documentation. So we actually have in Python itertools, we've got, let me just search for it. We've got a permutations function. And this is going to get all possible orderings of permutations. And they're using R instead of K, but this is essentially the same function. And we also have combinations. Combinations doesn't have, it's just, they think about it in the same way as we've been describing it. They're sorting their permutations, and they don't have any repeated elements. So here's the thing about itertools. That heaps algorithm that I wrote is going to deliver you faster permutations than will the itertools permutations. And that may be surprising at first, because it's like, well, this is in our Python standard library. You can import itertools and use their permutations function. But there's some other overhead on it. And in a lot of cases, I honestly, I'll write my own permutations in order to, solve a permutations problem I'm trying to solve. But usually, it's not so time consuming that it really matters. It's think about this in terms of combinations. Let's think about this in terms of combinations. Let's say you have some machine that has a bunch of switches and dials. Some of those dials take, numeric input, something between 0 and 1, or maybe they take, integer input between, 0 and 99. And if you have 10 dials, then you have a bunch of different ways that you can use that machine. When we get into when you get into machine learning, there are times where you are going to set up your machine, your machine learning model, with different tunings, right? You're going to there are these things called hyperparameters, and you are going to tune those hyperparameters to operate differently, and that is going to make a huge difference in the effectiveness of that model. And you want to, maybe this is obvious, you want to have the optimal settings on your machine learning model. And so you're going to come back to permutations and combinations. There's no doubt about that. This is something that, if in most cases, you're just going to use the iter-tool functions, but the reasoning, the understanding of what's happening with your combinations and permutations is really important. That's going to help you conceptualize a lot of types of problems. And that's kind of why we go into that deeper. Here's an intuition around a reductive approach, and notice that there are more optimal algorithms for this as well. At the end of the day, though, if you're getting combinations and permutations, you're probably going to use the iter-tools functions. Okay, that's the lecture for tonight. I might just record a video on the combinations function and post it along with the lecture for tonight. So stay on if you have any questions. I'm going to go ahead and stop recording. And yeah, have a great night. And,